Hello students, welcome back. Now let's go to section 3, radioactive decay model. It looks like this. You can write it as natural exponential function with a certain coefficient k, which should be negative here, minus k like this, so that we have indeed decay. Or instead of natural exponent, we use 1/2 as the base. And then instead of some coefficient times t, we use t over a certain capital T. And the latter model here is a little bit more popular because it turns out this capital T is called half-life. So precisely t years or minutes or seconds or hours, whatever, later, we have precisely the half the quantity. So this is basically what we have here. Let's put some space in between. So t over t, so 1 power. So what do we get? We just have half of q0. So initially we begin with q0, or maybe I'll start from there. Maybe I should start from there. So initially, this is 0 power, and the 0 power is always 1. So initially we begin with q0. And then let's move it here. Okay, all right. So initially we begin from q0 when we started the observation. Now capital T time later can be measured as years or hours or minutes or even seconds. We get half of the original. And then another t time later, capital T later, half again. Another capital T later, half again. So we have 1/2, 1/4, 1/8, 1/16, and so on. And we have this exponential decay. And the capital T is called half-life. There's a relationship between this k and capital T. And you can do that by setting up an equation like this. But a bit too complicated. Yes, you can do it, but a bit too complicated. So let's just move on. I just wanted to make sure that everybody understands this expression and that expression are interchangeable. Okay, all right. So much for theory, and let's go ahead with some example problems. The quantity of a radioactive material can be modeled by the following formula. Okay, this time we are using the exponential decay model with natural exponent t. Okay, all right. Estimate the initial quantity, the quantity after 2 minutes, and quantity after 20 minutes. Okay, just plug in t equals to 0, 2, and 20 and run your calculator. And you're supposed to get, well, 21.2 minutes, 18.43 minutes, and 5.22, excuse me, not minutes, well, this problem did not specify the unit of the radioactive material, so maybe it's grams or milligrams, I don't know. As time goes on, the quantity goes down. Eventually it'll go down very, very close to 0, but theoretical never actually reaching 0. After how many minutes later will the remaining quantity be 10 milligrams? Oh, okay. T is measured in minutes and quantity must be measured in milligrams, I guess. Okay, all right. So here, this part is going to be replaced by 10 and solve that equation. So it's an exponential equation like this. Can you solve it? If you take the logarithm right now, it's not going to work because of this. So flip it over and then isolate exponential and then apply logarithm. That's how you can do this kind of problem. So here we go. Solve for the exponential. All right, and then 10 over 21.2 will turn out to be this number. And whenever you are using calculation like this, put sufficiently long decimals in the intermediate step. So if your final answer should be, say, 2 decimal digits, my advice is 2 more and then use at least 4 decimal digits. The more the better, actually. And I use something like 6 decimal digits, 10 decimal digits many times, about 6 decimal digits as a matter of fact. That's Mathematical's default, actually. And then at the very end, bring it down to 1 decimal digit or 2 decimal digits, kind of like that. Okay, take the logarithm and flip over. We get about 10.7 minutes. That's about it. Easy, isn't it? Just a straight ahead exponential equation done by natural logarithm. How about the next problem? Okay, a little bit better this time and a little bit harder too, because we are using the half-life model. Also, this problem is coming from actual data. Americium-241 is a radioactive substance used in common household smoke detectors. The radioactive decay of americium-241 can be modeled by the following formula, and we have this. Okay, Q0 is the initial quantity, and time t is measured in years. So precisely at 432.2 years, did I say precisely? Excuse me. Nothing is precise in this kind of measurement. So approximately 432.2 years later, we'll have half the quantity. Okay, suppose that you have 10 milligrams of americium-241. Estimate the remaining quantity of americium-241 after 20 years, 200 years, 432.2 years, the half-life, 864.4 years, twice the half-life. Just plug in all those numbers in place of this t and then run your calculator. It should be easy computation, except that you have to repeat it 4 times. So repeat it twice, 20, 200, so we get 9.68 milligrams, 7.25 milligrams, kind of like that. But after 1 half-life, 432, then you have half of the original, so 5 milligrams. And then 2 half-lives, and you have 1/2 to the second power, so a quarter of the original. So you end up with 2.5 milligrams. Eventually, we'll have exponential decay going down like this. So first half, no big deal. Now, second half. How many years later? Okay, that's a little bit more worthy. How many years later will the remaining quantity be 7.0 milligrams? Okay, all right. Here's my model, radioactive decay model, and then the remaining amount will be 7.0 when the original was 10 milligrams, wasn't it? 10. Basically, I'm solving this equation. By the way, everything is coming from observations, so nothing is accurate. So I should be using this wiggly equality symbol like this all the time. Okay. How do you solve it? Well, I have to isolate this and then take the logarithm. So let's flip it over to the other side. So 7.0 over 10.0 is approximately equal to 1/2 to the t over 432.2. 0.0, 0.0, we don't really need any of those yet, so let's just keep those. And alright, we are using, okay, alright, that's fine. And then what do you do now? We have isolated this exponential here, so now it's good time to take the logarithm. So let's take the log. Left hand side, log of, log of 7/10. Oh, let's use decimal. Right hand side, log of 1/2 to the t over 432.2. I'm using decimal. Why am I using 1/2 here? Let's change it to 0.5 as well. They're the same. Okay. Now is good time to use this log rule to bring it out. So t over 432.2, you will get it out, and times log of 0.5. By the way, this expression, it doesn't look very good. Let's rewrite like this. Okay, instead of just getting equals to like that, let's repeat the entire equation here. So repeat this equation like this by taking the log rule. Take this one, this exponent, power, outside as coefficient. So what we have, log of 0.5, complicated, but it's a number. Log of 0.7, that too is a number. 432.2, that too is a number. So flip it all those to the other side. Then you're gonna get this. Log of 0.7 was on the other side as before, and then log of 0.5 was wrong key. We just flipped over, and then 432.2, that 2 is flipped over, and that goes to the numerator. So that goes to 432.2, and I guess a little bit bigger font will help. Punch your calculator in, and you're going to get the answer. So what do we have here? 432.2 log of 0.7 over log of 0.5. Punch your calculator and do your own computation and check. And I'm getting 223.4 approximately speaking. 222 years, approximately speaking. Did you get the same thing too? Let me check. Yeah. So, set up the equation, and then isolate the exponential, and then take the log. Once you take the log, remember the log rule. Power comes out as coefficient. Do you have time for another problem here? Maybe not, so I'll just breeze through. Suppose a quantity of a radioactive material becomes half of the original quantity in 3.4 years, so that's the half-life. So that's going to be the model, T divided by 3.4. And then plug in those numbers. 2 years, 5 years, 10 years, plug in those numbers and do your computation. Punch in the calculator, you get all those. How many years ago the quantity was 20.0 grams? So set up an equation, you're going to get a negative t value. You see, this was model, right? And then this is 20. So we have the second line. That's the equation to solve. Isolate the exponential and then take the logarithm. So divide by this 14.7, yeah, and then we get this digit. Isolated this exponential, so we can take the log. If you do that, the power comes out as coefficient like this, and dividing everything else, you're going to get t value like this. It's about negative 1.5, so about 1.5 years ago, it must have been about 20 grams. I went through the last problem really quickly, but it's okay, I think, because we went through similar problems before. That'll complete section 3, and let's meet again in section 4 in a separate video.